So I'm talking about efficient public trace and revoke scheme from standards assumption. And this is a joint work with Shweta Agrawal, Sanjay Bhattacharya, Damian Stelle, and Shota Yamada. So we worked on one-to-many window-receiver encryption. It means that in this framework, a center wants to encrypt a message to a large number of users. And so a trivial solution is that if you provide all the users the same key, then it works. But in this case, there is two problems. The first one is that if a user gives the key to a pirate, then the pirate can decrypt all the message, and we cannot identify the source of the leakage because all users share the same key. And the second problem is that when we want to revoke one user from the system, then we need to reset all the parameters because all the users have the same key. And so that's why traitor tracing and revoke or broadcast encryption are introduced to deal with these two problems. And now each user have one individual key. And we suppose that some user could give the key to the pirate who produce a pirate decoder and sell to the black market. And now the goal is that from the pirate decoder, how we can identify one of the traitor. And so the white box tracing level considers that the center is able to open the pirate decoder and get the pirate key. And from this pirate key, the tracer should be able to identify one of the traitor. A stronger security notion is about black box tracing. In this case, we suppose that the pirate decoder is obfuscated, and so the tracer can only interact with the pirate decoder in a black box manner. And so in this level, the strongest notion is full collusion. We suppose that all the user could be a traitor and could be collude to produce pirate decoder. This is a very, very strong notion, and actually there is no any efficient solution. A more realistic notion is inbounded collusion, and with the black box confirmation, it means that there is a bounded number of traitor, and the tracer have at least a suspect that user, and the goal is to identify the traitor, one of the traitor in this list. And so we also deal in this work with this bounded collusion model. And the second functionality is a revocation. So the goal is that the center can encrypt to all user except revoked user. And so most of the work deal with separately with traceability or revocability. And in this work, we deal with both functionality and this type of scheme called trace and revoke. And in the traitor tracing, the bottleneck is a tracing procedure with a very high complexity. And so it's a very nice property, it's a public traceability. In this case, the center can publish some public parameter, and from this parameter, anyone can do tracing. And so it's called public traceability. And in this case, the traitor implication can be publicly verified, and the overall system remains secure even if the tracer is corrupted. And it gives a very nice property of delegation. Thus now, because the tracing procedure can be done from public parameter, and so the center can delegate the tracing procedure to as many as he wants untrusted tracer. And so there is a very few scheme, trace and revoke scheme with public traceability. This scheme that's based on pairing from Bonnet Waters in CCS 2006. It supports a full collusion, but with large ciphertext size. It depends on n. It's square root of n, where n is the number of users. And even if the effective number of traitor in the system is small, the ciphertext size is always square root of n. And the last layer of Eurocrypt, there is a solution which based on general functional encryption or I/O. But we know that actually there is no efficient solution for general functional encryption and I/O. And when considering the bounded collisions, this gives scheme which the ciphertext size is still large, which is cubic on the number of revoked user and number of traitor. And so our approach is that we start from inner product functional encryption instead of general functional encryption. And we know that for this particular case of functional encryption, the inner product functional encryption, there are many efficient solutions. And so we will give a sample transformation from inner product functional encryption to trace and revoke. And we also require only a weak security level of the underlying inner product functional encryption. And this gives us to improve the security, the efficiency. And at the end, we get the scheme that's based on standard assumption. Based on DDH, the known scheme does not support public traceability, and so we add the public traceability. Based on Pioneer scheme, actually there is no concrete solution, and so we get a trace and revoke scheme with public traceability. And based on learning with error assumption, so there is a traitor tracing scheme, but does not support revocation. And as we mentioned, they scheme from the general and functional encryption. And so we get a trace and revoke scheme with public traceability, which improve the efficiency. So now I will explain the main idea in the transformation from inner product functional encryption to trace and revoke. So we know that in functional encryption, in generalized classical encryption, in classical encryption, so the decryption return the whole message. Or in the functional encryption, we can specify a partial information on the plain text. And so each secret key is associated to a function f, and then the decryption gives f, the function f on the plain text m. And for the inner product, modulo p here, and so the secret key is associated to a vector x. And the ciphertext encode a vector v, and the decryption, the function f, is the inner product function. It means this gives the inner product of x and v. Now, how we can get a revoke scheme? The simple idea is that we rewrite the message m as the inner product of x and m with the v divided by inner product of x and v. For any x and v different to 0. And so the idea is that we choose vector v in such a way that is the inner product of x and v equal to 0 for all the revoked users. And so we encrypt the message mv. And so revoked user cannot decrypt, cannot do division by 0. So concretely, from the inner product functional encryption, so in our construction, for each user ID, then we will generate a random vector x ID associated to ID, and then simply runs the key generation of the functional encryption. And then to revoke a set R, then we will choose a vector VR that is orthogonal to all the revoked users. And then we encrypt the message M times VR. And then all the revoked user can do a division by 0 and can decrypt to message M. And the revoked user cannot decrypt. Now we explain how you can do tracing in this construction. And so the model of tracing is following. An adversary A can ask the secret key for any ID of his choice. And then from this secret key, the adversary will produce a pirated decoder. And now the tracer will interact with this pirated decoder to trace back one of the traitor. We reckon in the encryption, in our scheme, we encrypt with the vector m times vr. And now we win. What happened if we add another vector vs in the plain text? If we add this vector in the plain text, then when we do decryption, this will give the message m with an additional term. And now we can play on this additional term for tracing. So the main idea is that in the normal ciphertext, the VS is orthogonal to XID, and then this is cancelled out, and then the decryption gives back the message, correct message M. And in the proof ciphertext for tracing, this is different to 0, and then this not give the original message M. And from this difference, we can trace by traitor. And concretely, we were working on the black box confirmation, and thus we have a suspect set S. At the first step, we choose on the vector VS, which is orthogonal to on the user in S, and we encrypt with this vector VS plus MVR. And thus, all the non-revoked user, as we explained in S, can correctly decrypt the message M. And from this starting point, we can apply the linear tracing technique. Now we can remove users one by one from this suspected set S. And each time we remove one user I. And so we get the SI. And now we encrypt, we do the same thing, but for the set SI. And so all the non-revoked user in SI can still decrypt. And so we can show that if I is not a traitor, then the pirate does not have the key of the user I. And then the pirate cannot distinguish a ciphertext for SI and a ciphertext for SI minus 1. And thus, if there is a gap in probability of decrypting message M from these two sets, necessarily I is a traitor. And at the beginning, we see that all user in S decrypt to M. Pirate decoder will decrypt to M. And at the last step, none can decrypt. And so it means that the message M we can show is independent from the viewer pirate decoder. And then the probability to decrypt M is negligible. Thus, there is a gap step where the probability in decrypting these two consecutive tests is non-negligible, and we can trace by the trader. And now we will explain how we can relate the security of trace and revoke scheme to the security of functional encryption. We call that in the trace and revoke scheme, the adversary asks the key query for an ID, and adversary will get the secret key SKID. And in our scheme, SKID is produced by the following. First, a vector XID is randomly generated, and then we call the functional encryption on this vector XID. It means that the adversary does not control this vector XID. It's randomly generated. This is very different from functional encryption, because in functional encryption, the adversary can ask the secret key for any XID of his choice. And thus, we can prove the security of trace and revoke scheme from the random key security for functional encryption. And in this model of security, the adversary will get secret key H for random vector H. Now the adversary cannot choose vector S H. S is 1. And so the security of trace and revoke scheme can be based on a weaker security level, random key security of inner product function encryption. And so this gives the motivation to improve the known scheme in this random key model. And we show now how we can improve the LWE based inner product function encryption. So for the inner product function encryption proposed last year in crypto, so Agrawal, Libe, and Stele, first they give a version of LWE for vector is essentially the same LWE encryption, but instead of one vector secret key, now is they use many secret key, and so the public key will be a matrix, and they use this matrix instead of one vector to encrypt, and thus instead of encrypt one value, now one can encrypt a vector. And so the decryption is done the same way. From Z, we multiply with C1, do the difference with C2, and get back this vector Y. And this version modulo P. And now from this encryption for vector is very simple to get a version of inner product function encryption. Simply from a vector X, we associate to this vector X a secret key Zx is simply X times the master key Z. Now using Zx to decrypt instead of Z, we will get the inner product of X and Y instead of Y. So now for the adversary can ask for many vectors which come to a vector X. And so the adversary can get a matrix X, and the adversary learn X times Z. So in the view of the adversary, they know X. So the matrix Z can be seen, the column of Z can be seen as distributed on the shift kernel lattice lambda, which is orthogonal to X. And now for the adaptive security, so there is an attack that the adversary can ask the vector X, which is a dependent modulo P, but independent on integers. And so to avoid this attack, they need to work with a slightly modified X bar, so that essentially X bar is equal to X. But in case X is linearly dependent modulo P, then X bar is also linearly dependent over integers. But this way we can see that this way lead to a matrix X bar quite large. And thus, the smoothing parameter of the lattice lambda could be very large. And this is exactly the source of inefficiency. And if we use directly the scheme, then we will get a trace and revoke with the ciphertext size cubic on the number of traitor and revoked users. Luckily, now we only need the random key security. And in this case, all the vector X is randomly chosen and in ZP. So we can, instead of choosing X random in ZP, we can start with X bar, come from a small Gaussian distribution, and then modulo P is give also X randomly chosen in ZP. It means that now X bar come from a small Gaussian distribution, and then from previous solution, result at example 13 from Agrawal Gen 3 Halavi Sahai, they show that the smoothing parameter of lambda is small, and thus all the parameters can be improved. And the result of trace and revoke have the size essentially linearly dependent on the number of revoked user iterator. So to conclude, we give a transformation from inner product functional encryption to trace and revoke, and this gives efficient scheme from standard assumption, and this gives also the motivation to construct more efficient in the product function encryption and find more application of this primitive.
So nobody's asking questions, so I think I thought I should ask one. So the number of users you considered. So when you are broadcasting, is it constant before
No,
known
no,
beforehand, or anyone can
no.
dynamically join?
So it's the number of user can be very large. We essentially here is nice identity-based encryption because for any string ID you can we can generate a secret key for ID.
Yeah, but it need to be known
No, no,
beforehand, or
no, it do not need to be fixed beforehand.
okay.
Yeah.
Thanks.
It could be generated dynamically.
So I'm Ni from Oregon State. So for in the slide setting you have A. So how did you choose A and IE public or just have to keep private? In the slide setting, net private. Yes. How can you choose A? The metric A here.
I see random matrix.
And this is the
And this that is a small secret key.
and this is the have to be private, have to be keep
No,
private.
no, it's public.
Oh, I see. Yeah, thank you.
Thank you.